Have you ever watched a quarterback throw a perfect spiral or a firework burst right at the top of its flight and wondered, how? Well, it might look like magic, but it's not. It's pure, elegant physics. Today, we're going to dive into the science that governs literally every object that gets thrown, launched, or shot through the air.
So let me ask you a question. What could a basketball sailing toward a hoop, a firework climbing into the night sky, and a satellite circling the Earth possibly have in common? I mean, they seem totally different, right? Well, it turns out they're all playing by the exact same set of rules, a surprisingly simple universal principle.
And that secret principle, it's called projectile motion. Think of it as the hidden code behind the curve of everything, from a baseball leaving a bat to a meteor streaking through our atmosphere. At its core, it just describes the path of any object when the only major force acting on it is gravity.
And that beautiful, predictable curve that everything follows, it's got a name, the trajectory. Every single projectile has one, and by the end of this, you'll see just how we can predict it with incredible accuracy.
Now, the key to this whole thing, the one rule we have to agree on, is that we're looking at motion where gravity is the star of the show. For now, we're going to ignore other things, like air resistance, just so we can get to the pure physics at the heart of it all.
So how in the world do we crack the code of that complicated-looking arc? Well, here it is. This is the big secret, probably the single most important idea you need to take away from this. You don't analyze the arc as one complex curving motion. No, you break it down into two completely separate and much, much simpler motions.
And this idea right here is the key that unlocks absolutely everything. The horizontal part of the journey and the vertical part of the journey are totally independent. They don't affect each other at all. What happens going up and down has zero impact on what happens going side to side, and vice versa. This is the whole game.
And here's what that independence looks like in the real world. On the one hand, you've got the horizontal motion. It's super simple. The object just cruises along at a constant speed. No acceleration, no drama. But on the other hand, you've got the vertical motion. Now that's a different story. Its speed is always changing, all thanks to gravity's constant downward pull, which we call g.
This diagram really shows it perfectly. See that horizontal arrow, the Vx? Notice how it stays the exact same length the whole way through? That's our constant horizontal speed. But look at the vertical arrow, the Vy. It starts out big, shrinks to nothing at the very top, and then grows again on the way down. These two things are happening at the same time, but the only thing they share, the one thing that connects them, is time. Okay, so if we've got these two simple, separate motions, how do we actually describe them with math? Well, lucky for us, physicists have a standard set of tools for any time there's constant acceleration. So let's open up the toolkit. First, let's meet the variables. People often call them the SUVAT variables. We've got S for displacement, or distance, U for the initial velocity or starting speed, V for the final velocity, A for acceleration, and T for, you guessed it, time. Knowing what these 5 things represent is step 1 to solving pretty much any motion problem. And here are the tools themselves, the 3 main kinematic equations. Now, I know they might look a little scary, but just think of them like recipes. If you have a few of the ingredients, our SUVAT variables, you can use one of these to find whatever you're missing. That last one is especially cool. It's like a shortcut when you don't know or even care about the time.
All right, enough theory. Let's get our hands dirty and see how this actually works in the real world. We're going to take our big idea about independent motions and our shiny new toolkit of equations and put them to the test on a classic example, launching a firework.
Okay, here's the setup. We've got a fireworks shell, and it's launched at a speed of 70 meters per second at a really steep 75-degree angle. The fuse is timed to make it explode at the very tippy top of its arc. So, our mission, should we choose to accept it, is to figure out exactly how high it goes and how long it takes to get there.
So what's our game plan? Well, we use our big secret. We split the problem in 2. First, we're going to focus only on the vertical motion. Why? Because the peak of the flight, that highest point, is a purely vertical thing. It's the exact moment the upward motion stops and the vertical speed is 0. Once we figure out the time it takes to get there, we can solve for anything else we want.
And this is exactly why our strategy is so powerful. As the quote says, the time something spends in the air is all about its vertical journey. The horizontal part, it's just along for the ride, for however long the vertical motion lets it fly.
So, after we break down that initial velocity into its up and down and side to side parts, we can use our timeless equation.
We know the final vertical velocity at the very top is 0, and that lets us solve for the height. And the answer is an incredible 233 meters. To put that in perspective, that is taller than a 60-story skyscraper.
So how long does it take to reach that crazy height? Well, for that, we can grab our first tool, v equals u plus at, to find the exact moment the vertical velocity hits 0. And we find out the fuse needs to be set for precisely 6.90 seconds. It's just a perfect example of how we can use physics to predict the future.
And look, this isn't just about fireworks. Once you get the hang of projectile motion, you seriously start seeing it everywhere. It's this fundamental code that describes the world in motion all around us, from sports to nature, and even, as we're about to see, to outer space. Take a golf shot, for example. On the left, you've got a low, fast shot. On the right, a high, looping shot. They follow completely different paths, they reach different heights, yet they land in the exact same spot. How on earth is that possible? Well, the secret is all about a trade-off. The high looping shot has a huge vertical velocity, so it spends a lot more time in the air, but it doesn't travel forward very fast. The low shot has a massive horizontal velocity, but it's back on the ground in no time. And sometimes those two different effects can cancel each other out perfectly to give you the exact same distance.
Now, let's take this whole idea and push it to its absolute limit with one of the greatest thought experiments of all time, Newton's cannonball. So imagine you're on a mountain so tall it pokes out of the atmosphere. You fire a cannonball, it follows its trajectory, and it lands. You fire it faster, it goes farther. Simple enough. But what happens if you fire it really, really fast?
And this is the mind-blowing question. The cannonball is always falling toward the Earth because of gravity. We know that. But the Earth isn't flat, it's a sphere. So if you can launch that cannonball with enough horizontal speed, as it falls, the ground itself literally curves away from underneath it. So what happens if those two rates, the rate it falls and the rate the Earth curves, match up perfectly?
You've created an orbit. And this is the big reveal. A satellite in orbit isn't just floating up there. It's actually in a constant state of free fall. It is perpetually falling toward the Earth, but it has so much sideways speed that it continuously misses the ground. The simple physics of a thrown ball when you scale it way, way up explains the motion of satellites and even the moon.
So, there you have it. We went from a simple curve to a stable orbit, all using just one core idea, breaking a complex motion into two simple ones. Projectile motion isn't just some formula in a textbook. It's a beautiful, fundamental piece of the universe's instruction manual. It really makes you wonder, right? What other elegant, hidden codes are all around us, just waiting to be discovered?